Welcome to The Explainer. You know, in the world of making semiconductors, the big fight used to be about stuff you could actually see, microscopic particles. Well, that whole game has changed. Now, the real enemy, the biggest threat, is totally invisible. We're talking about a battle happening down at the atomic level. All right, so here's how we're going to break this down. We'll start with this invisible threat, then get into the nitty-gritty physics of how it causes failures, and of course, the very real business costs. After that, we'll get into a totally new way to solve this, a structural solution, and check out the real-world bottom-line advantages it brings. So for like decades, right, the whole industry got really good at one thing, keeping chips clean. We're talking about filtering out microscopic dust, all that visible gunk. But that whole frontier, it's moved. The real war is now being fought at the atomic scale. And you know what? The old rules just don't work anymore. And this is the question that should be keeping every manufacturing engineer up at night. I mean, what do you do when the threat is so small it just sails right past all your defenses, all your filters? This isn't some minor issue, it's a direct assault on the most fundamental parts of our chips, like those supercritical MOSCap structures. This right here, it just lays out the shift perfectly. Look, we're not just fighting dust bunnies anymore. The real battle is against these rogue atoms, individual atoms that get stuck right where the magic happens, at the most critical interfaces in a device. And believe me, that's exactly where they can cause the most chaos. Okay, so you're probably wondering, how can something so small, something invisible, actually cause a catastrophic failure? Well, to get that, we've got to zoom way, way in. We're going down to the boundary layer of the chip itself. This is the place where either everything works perfectly or it all falls apart. So in the industry, there's a specific way we measure this problem. It's a metric called interface defect density, or just DIT for short. Honestly, you can think of it like a report card for the atomic level, a quality score. It tells you exactly how many of these tiny but absolutely devastating flaws you have. Things like stray atoms, or even just gaps where an atom should be. All of which messes up that perfect interface structure. And these little defects, they don't just sit there. Oh no, they kick off this insane, catastrophic chain reaction. First, they start piling up at that critical interface. Then they form what we call traps, which basically snag and disrupt the flow of electricity. From there, you get current leaking out where it shouldn't be, and before you know it, poof, the whole insulating layer breaks down. And the end result? A chip that performs like garbage and is basically a ticking time bomb, destined to fail. And look, don't just take my word for it. This isn't some theoretical problem we're dreaming up. The industry's own roadmap, the IEEE IRDS, the Bible for this stuff, says it loud and clear. Our old tools, the ones we've relied on for years to find particles, they're basically blind to these new threats, anything smaller than 5 nanometers. So we're left fighting an enemy we literally cannot see. All right, so we've talked about the physics, but a problem this deep, this fundamental, it's not just a science experiment. It translates directly, and I mean painfully, into a massive financial headache for anyone trying to make these chips. Yeah, when your DIT score is high, you're looking at a trifecta of business nightmares. First, it absolutely crushes your manufacturing yield. Second, it tanks the reliability of your products out in the real world, which means angry customers and expensive returns. And third, it jacks up the cost of every single good die that actually makes it off the line. And the financial hit from these tiny atomic defects, it's just staggering. It's hard to even wrap your head around. Think about it. In one of these multi-billion euro fabs, a tiny, almost insignificant sounding 1% drop in yield, that can wipe out millions of euros in revenue annually. Suddenly, every single wafer you start is a massive, high-stakes gamble. So, the billion-dollar question is, how do you fight back against something like this? Well, the traditional way has always been to kind of put a Band-Aid on it. You apply a patch, some kind of passivation layer, but that's just covering up the symptoms. It does absolutely nothing to fix the real underlying structural problem that's causing all the defects in the first place. And that leads to a really powerful idea. What if? What if instead of just patching the cracks, you could rebuild the entire foundation? Make it structurally perfect right from the start? Well, that's exactly the idea behind this brand new approach. It's called SisuSemi atomic level purification, or ALP for short. And this thing is a total game changer because it's designed to do just that. Rebuild the interface structure, make it perfect during the manufacturing process. So what's the actual difference? I mean, what does it do? Okay, check this out. Before ALP, you've got this messy, disordered, amorphous interface. It's chaotic. It's just begging for defects to form. But after ALP, it transforms that mess into a beautiful, highly ordered crystalline structure. It's nearly perfect. See, this isn't a band-aid. It's a fundamental fix. It gets rid of the root cause of the problem once and for all. Okay, that sounds great in theory, but what does a structural change like that actually get you? Where's the proof? Let's dive into the hard data, the measurable results that really matter to the bottom line. All right, get this. In a real-world case study on MOSCap wafers, ALP slashed that critical DIT metric by a staggering 42%. I mean, that is a direct, massive improvement in the actual electrical quality of the chip's most important interface. And that massive improvement in quality, it had a huge knock-on effect. It resulted in a 67% reduction in leakage current. Seriously, for any engineer out there who cares about power efficiency and reliability, that number is an absolute game changer. So let's bring it all back. Those incredible technical wins, they directly map to solving those three big business nightmares we talked about earlier. A better interface, that means higher yield. More reliable devices, that means fewer field failures. And when you put those two together, you get a lower cost for every single good die you produce. Simple as that. So at the end of the day, when you fix the problem at its atomic root, the competitive advantage you get isn't just a little bump. It's not incremental, it's foundational. It's literally the difference between slapping some paint on a cracked foundation and building a brand new, perfect one from the ground up. So for anyone out there trying to navigate the insane economics of modern chip manufacturing, really understanding the difference between a patch and a true structural fix, well, that's something that's worth every single atom of your attention.